Hey math fans, Alex here, and coming to you today with the Moivre-Laplace Theorem. To start off with, let me just give you a little bit of motivation for this theorem. So suppose that x is a random variable that represents the number of heads from a fair coin, and consider 1,000,000 Bernoulli trials. And we want to find the probability that x is bigger than or equal to 525,000 heads. Okay, well, since this is a binomial distribution, and since this is also a fair coin, that means that p is equal to 0.5. So technically what you would have to do is you would have to sum from k equals 525,000 all the way to 1,000,000 of, let's see, 1,000,000, choose k, times the probability of success raised to the k times 0.5 times 1,000,000 minus k. I don't have to tell you how awful that is. Now, you might recall that sometimes we were allowed to approximate this using a Poisson distribution. So are we allowed to say that this is approximately equal to a Poisson? The answer is no, because p is way too big. So the answer is no. Remember, for a Poisson distribution, we need p small and n big. Clearly the number of Bernoulli trials is big enough, but p is way too big to make any kind of useful approximations. Okay, so what are we supposed to do? Are we supposed to actually compute like hundreds of thousands of different sums? The answer is no. Remember, in the last video, we learned about this handy-dandy thing called the normal distribution, which is a continuous random variable distribution. And we're going to learn how the binomial, if you have enough Bernoulli trials that you're summing over, can actually be approximated very well using the normal distribution. So here's the de Moivre-Laplace theorem in its entirety. It says, given n independently identically distributed Bernoulli random variables, x1 all the way to xn, go ahead and let Sn be the sum of those, and we're going to define a new random variable Sn star, which is going to be Sn minus the expected value of Sn, all divided by the square root of its variance. Well, then it turns out that the probability that Sn star is between a and b, as n goes to infinity, is actually equal to the integral from a over b of the probability density function of the standard normal distribution. And I should specify that this holds for any a and b real numbers. It doesn't matter. So if you want the probability, if we go back up here, that x is between any two possible values, eventually you can approximate that using the normal distribution. Okay, now that's a tall order, and this proof is going to take some time, but I thoroughly believe that we're going to get a lot of useful stuff out of this proof. Okay, so let's go ahead and start. The first thing to know is that Sn is a sum of Bernoulli random variables, which is just 1 if it's a success and 0 otherwise. So it's going to be a sum of 1s and 0s that represent the total number of successes in n Bernoulli trials. Hopefully that sounds like a binomial distribution, because that's exactly what it is. So Sn is really just a binomial distribution with parameters n and p, so we already know what the expected value and variance are. We calculated that in a previous video. So we have that the expected value is np and the variance is npq. So then what we can do is we can more distinctively characterize Sn star. Remember that Sn star was Sn minus the expected value of Sn, which remember was given by np, all divided by the square root of the variance. Okay, but we remember what the variance is. The variance was npq. Okay. Now, I claim that Sn star is actually a discrete random variable. Okay, why is it a discrete random variable? Well, it's going to be Sn minus a constant divided by a constant, and Sn is discrete. Sn takes on values that represent the total number of successes. And there could be anywhere from 0 successes all the way up to all successes, all n successes. Okay, so we're going to go ahead and let an element of Sn star be represented with the letter z because of the normal distribution. And z is going to be equal to k minus np all divided by the square root of np cubed, just so we know what a typical element looks like. Okay, and we're going to go ahead and use that in this proof. So we're going to make 3 approximations in order to be successful here. The first approximation we're going to use is Stirling's formula, which recall that Stirling's formula gives us a way to approximate the factorial. And the factorial of y is asymptotic to square root of 2 pi y times y to the y times e to the minus y. So that's our first approximation. If you want a proof of that, just look up a video. Many people proved it many different ways. You could take ln, you could take the natural log of both sides, for instance, and use some approximations there. We're also going ahead and assume that k divided by n, the total number of successes divided by the population, is asymptotic to the probability of success p. Okay, likewise, we also have that n minus k divided by n is going to be asymptotic to q, which recall that q is just 1 minus p. Okay, and the third approximation we're going to use is actually an approximation for the natural log of 1 plus y, where y is a very tiny number. And due to the Taylor series, which is an alternating sum, you can show that this is asymptotic to y minus y squared over 2. Technically, it's equal to this plus some other terms, which are going to be bounded by y cubed, which is going to be really small. So I'm actually going to save the proof of 3 at the end, and I'm not going to go over it in the video. It's just going to be in the notes if you want to take a look. But I am going to go ahead and prove 2, because it kind of gives us a rough estimate of the law of large numbers, if you're familiar with that, or the central limit theorem. Okay, so let's just prove 2 really quickly. So the idea is we want to show that k over n is asymptotic to p. So remember that if z was a typical element that looked like this, I can very easily solve for k, right? I can multiply both sides by the square root of npq and then add np to both sides. So clearly k is equal to z times the square root of npq plus np. Okay, now I'm going to divide both sides by n. Let's go ahead and do that. So if I divide both sides by n, divide this by n, and I divide this by n, then I get that. Then k over n is going to be equal to what? Well, the square root of pq is going to stay as it is, but this is going to be z times the square root of pq divided by the square root of n plus p. And then it's clear that if I take the limit of k over n as n goes to infinity, so the limit as n goes to infinity of k over n has to be the limit as n goes to infinity of this z square root of pq divided by the square root of n plus p. Okay, but the limit as n goes to infinity of something with an n in the denominator, that's going to be 0. Okay, so then we just get that this is p. So a very useful approximation. And as an exercise, you should prove this result kind of on your own. It's very similar. Okay, so just a reminder of what we're trying to do here. We're trying to figure out what the limit as n approaches infinity of the probability that Sn star is between A and B. So that's our goal. So maybe since Sn star is a discrete random variable, we should figure out what's the probability that Sn star takes on the value z. Remember I said a typical element is going to be some z. Well, what is that probability going to be? Okay, well, if you just look back up to what Sn star was defined as this. Now, Sn star is only going to be z whenever Sn is k. So it's only going to take on the value z whenever there are k successes in n trials. Remember I said that it's essentially a binomial distribution. So the answer is that this occurs when the number of successes is equal to k. So we get that the probability that Sn star is equal to z is equal to the probability that Sn is equal to k. And we know exactly what that is because it's binomial. That is exactly n choose k, p to the k, and I'll go ahead and say q to the n minus k. Okay, that's not so bad. The problem is if n is obscenely big, this binomial coefficient presents a big problem. Because if you remember, this was equal to, the binomial coefficient was equal to n factorial divided by k factorial n minus k factorial times p to the k and q to the n minus k. Okay, so that is going to be a pain in the butt to approximate. However, we have a tool at our disposal that allows us to approximate factorials. Okay, so we're going to go ahead and use the first of our approximations. That was Stirling's formula. And we get that by 1, what we have is that this quantity, I'm just going to write it out. So this p to the k, q to the n minus k, that's going to equal, big deep breath here, that is going to be asymptotic, I should really say asymptotic to the following. This is going to be the square root of 2 pi n, n to the n, e to the minus n, all divided by, this is going to be a lot, square root of 2 pi k, k to the k, e to the minus k, times the square root of 2 pi n minus k, n minus k to the n minus k, e to the minus n minus k, times p to the k, q to the n minus k. Now, you'll notice right away that a lot of nice things happen and cancel out, but I'm going to go ahead and leave it to you as a small exercise to show that this is going to equal 1 over the square root of 2 pi times the square root of n divided by k times n minus k times np over k to the k times nq divided by n minus k to the n minus k. So please pause the video, attempt to show that before moving on. Okay, so we wrote this, this term right here as the product of three things. First thing is really simple. It's just 1 over the square root of 2 pi, which, by the way, is what we wanted. And then I'm going to go ahead and label this guy as star, and I'm going to label this guy as double star. And we're going to figure out what both of those are in due time. Let's focus on star because it is the easier of the two, at least in my opinion. So let's figure out star. So we're trying to figure out what the square root of n divided by k times n minus k is. Okay. And what I'm going to do is I'm going to divide the numerator and denominator by n. So this is going to be equal to, let's see how I want to write this. Okay, so we're going to divide this by n, we're going to divide that by n. So then this is going to equal the square root of 1, which I don't even need to write, divided by the square root of k over n times n minus k. All right. Now what I'm actually going to do is I'm going to pull out an n from this expression. Okay, so this is going to get me 1 over the square root of n times k over n times 1 minus k over n. You'll notice that everything now is expressed in terms of either n or k over n. But here's where we're going to use our second approximation. This is going to be asymptotic. Let's see what color I used. Yeah, this is going to be asymptotic to what? Well, by our second approximation, remember the one that we just proved, k over n is asymptotic to p. So this is going to be asymptotic to 1 divided by the square root of n times p times 1 minus p, which remember was q. Okay, so I'm actually going to go ahead and box that. Weird box, but okay. So not too bad for that one. Let's focus on double star now. Okay, so how are we going to do double star? Well, the first thing I'm going to do is I just want to note up here that we have a lot of terms that look like np divided by k and nq divided by n minus k. So we should probably figure out an expression that kind of relates k as well as np. So we're actually going to do that by recalling this. Okay, so remember, a typical element of Sn star looks like that. So we're essentially going to copy that down. Okay, so a lot of setup here, but recall that z was equal to k minus np divided by the square root of npq. But that means that k equaled z times the square root of npq plus np. All right. Why am I doing that? Well, we want np divided by k. Well, we're not going to get that, not directly, but what we can get is k divided by np. Okay, so we're going to take this k, and now I'm going to go ahead and divide it by np. K divided by np is going to now equal this term divided by np plus np divided by np. And after simplifying the radical, you're going to get that this is going to equal z times the square root of q divided by np plus 1. Okay? And similarly, if we're going to find an expression for k divided by np, we should probably find an expression for n minus k divided by nq. So similarly, we get that n minus k divided by nq is going to equal that's going to equal 1 minus z times the square root of p divided by nq. And I will leave that to you as an exercise to verify that. Okay. So, what do we want? A lot of things, I'm sure. But right now, let's just focus on trying to figure out what this is. Well, that's not going to happen. But I will tell you what will happen. We're going to find the natural log of all of that junk. And this is where natural logs become incredibly useful. So I'm actually going to copy this. Let's see if I can do it. Yep. We're going to go ahead and we want to find, well, I'll just go ahead and copy it as is. We want that. So instead, we will find the natural log of this expression. And actually what we're going to do is we're going to find the natural log of, get ready for this, k over np to the negative k. All I did was I just flipped it, but then raised it to the negative 1 power. Okay, so that's certainly okay to do. Times, same thing, n minus k over nq raised to the negative n minus k. Okay? So that's what we're trying to find instead. But a very useful property of logs is that the log of a product is the sum of the logs. Okay, so this is going to equal natural log of k over np to the minus k plus natural log of n minus k over nq raised to the minus n minus k. And if I'm taking the natural log of something to a power, that power just goes right in front as a coefficient. Again, another property of logs. So this is then going to equal minus k times ln of k over np minus n minus k times the natural log of n minus k over nq. And just a reminder that this is the natural log of what I've called double star. And then after we find that, then just exponentiate. Just take e to that, and then we're done. Okay, so easier said than done. However, we do have expressions for k and n minus k. So k and n minus k can be found by going up to here. Okay. So I'm going to go ahead and use that. So let's see. K was, let's see, z times the square root of npq plus np. This is times the natural log of k over np. And then if this quantity right here, if that was just k, you can find n minus k pretty easily by taking n minus this expression right here. And what you're going to get is you're going to get that this is minus, this is going to be minus nq minus z times the square root of npq times the natural log of n minus k divided by nq. Okay, so again, I know that none of this looks like it's any better, but it's at least manageable. because we're about to use our last approximation. Okay, so in order to use our final approximation 3, we need this to be in the form natural log of 1 plus something really small. Okay, but we computed what k over np was. We computed what that was above, so I'm actually going to maybe highlight that in yellow. So remember that this and this were already computed above as right here and right here. So we're just going to plug those in now. Okay, so this is going to be minus z root npq plus np times ln of 1 plus c times the square root of q over np. Okay, minus nq minus z times the square root of npq times the natural log of, and I believe this was 1 minus, so I'm actually going to write this as 1 plus a negative z times the square root of p over nq. Okay, and now we can actually write this using 3 as our approximation. So this is going to be asymptotic to, and I'm going to give myself some room here. I'm actually going to write this on 2 separate lines. So this is going to be asymptotic to by 3 the following. This is going to be minus z square root of npq plus np times this stuff. Okay, but this stuff was written in the form 1 plus y, where y is really small. Okay. So this is going to be equal to that y value minus y squared divided by 2. So it's going to be z squared over 2 times q over np. Not to get ahead of myself, but you should start to get really excited because this minus z squared over 2 is in the normal distribution. All right. Now, all these minus signs are kind of tripping me up, but I guess we can roll with it. Okay, so this is then minus nq minus z square root of npq times y minus y squared over 2. Okay, well, y is going to be that negative, so it's going to be negative z times the square root of p over nq minus y squared divided by 2. So that's minus z squared over 2 times p over nq. Okay, so the first thing that I'm going to do is I'm going to factor a negative sign out of this expression. So I'm just going to go ahead and do that now. So that's going to become a plus, and then that's a plus, and that's a plus. And that's a plus that we did that. The second thing that we're going to do is we're just going to have to multiply everything out, and we're going to have to combine terms with a z in them. Okay, so there's just no easy way to do this. You're just going to have to kind of FOIL this out. And when you do, this is going to equal negative z squared over 2 times p plus q plus there's going to be a z cubed divided by 2 times a whole bunch of junk. Q over np minus p times p over nq. Okay? So that is going to be a big old exercise for you to just FOIL all that out and just make sure that that is looking good. But now we're so close. You see it? P plus Q is 1. The sum of the probabilities of success and failure, they have to sum up to 1. So that's 1. This is not anything useful. However, it is asymptotic to 0. Or in other words, this is equal to 0 as n goes to infinity. Why? Look right there. That's as simple as I'm going to make it. So that expression just goes away. Thank goodness. And, you know, if we added more terms to our natural log approximation, they would similarly cancel. So we're in the home stretch almost. This is going to equal, or at least I should say probably this is asymptotic to minus z squared over 2. All right. So now that that is double star, I am going to, well, that is really the natural log of double star. So since this is the natural log of double star, it stands to reason that double star is actually equal to e to the minus z squared over 2. And now I'm going to box that. Okay, now we are finally ready to put everything all together. Okay, so I'm going to go ahead and do that, and then I'll be right back. Okay, so I went ahead and plugged in for our lengthy expression up here. 1 over square root of 2 pi times the product of these terms is asymptotic to 1 over square root of 2 pi e to the minus c squared over 2 times this mystery, 1 over the square root of npq. Let's solve that mystery right now. So here's kind of the idea. Remember that we're trying to figure out the probability that Sn star is between A and B. Right now, A and B could be whatever on this real number line. Just pick any 2 points with A less than B. And since this is a discrete variable, discrete random variable, it takes on finitely many values. And the smallest value that it's going to take on, the smallest this could possibly be, is when you plug in 0 for k. You have no successes, and then that is going to be minus np divided by the square root of npq. That might not even include a at all. That doesn't matter. Okay, but we're going to go ahead and plug it in right here. And then the next value of k would be 1. Why am I telling you that? Well, it turns out that if you take the difference between k equals 0 and k equals 1, they're all going to be uniform. The distance between any two of them is going to be the same. And it turns out that that distance, which we might as well just call the change in the z values, remember because these are z, actually I might as well say the change in the z sub k values, you're going to get that that's exactly equal to our mystery friend, the square root of 1 over npq. That's interesting. Think about integration for a second. Think about Riemann sums. That's our eventual goal. And now let's think about what happens as we let n go to infinity. As n goes to infinity, this term is approximately is proportional to the negative square root of n. Right? This is about it's proportional to negative square root of n. And as n approaches infinity, this term right here is going to move perhaps to a point that is to the left of a. And this last term, which just happens to be nq divided by npq, where k is maximal, if k is equal to n, that's what you get, that might move all the way over to the right of b. Maybe not. If not, fine, just keep increasing n. You're eventually, by what's called the Archimedean principle, you're eventually going to reach a point where a and b are sandwiched between the left and the right values of z. Why is that useful for us? Well, now we know exactly how to find this probability in the discrete case. Okay? This is going to equal the sum over, we'll say, values of k, where k might equal, we'll say, j to L. I'll explain what j and L are in just a second, of our little friend here. But this time, instead of z, I'm going to put this as z sub k squared over 2 times 1 over the square root of npq. But remember, I called that delta z, so let's go ahead and switch over to that. This is delta z sub k, where j and L are respectively the smallest and largest values of k satisfying this little inequality. Because again, we really want to sum over all these values. So if you were asked to do this as a problem, which you never will be, what you're going to do is you're going to find all these values, find the probabilities at each of these points, and then sum all of them up. Right? That's hypothetically what you would do. But you might imagine that as n goes to infinity, those gaps are going to be even smaller, and you're going to be summing even more of them. So this is a Riemann sum. And now the last thing that I'm going to do, because we didn't want this, we actually wanted the limit as n goes to infinity. So thus, the limit as n goes to infinity of this probability is going to be the limit as n approaches infinity of a Riemann sum. 1 over square root of 2 pi e to the minus z sub k squared. That's our tag. And, well, times delta z sub k. Punchline, that is just the integral. Now, as n goes to infinity, really the distance between what we call maybe z sub j and z sub l is going to get so small that we might as well just sum from a to b. There's going to be no distinguishable measure between a and those values and b and those values. So really we can just say this is an integral from a to b of our function. We don't need the tag anymore, times dz. And that is the proof of the de Moivre-Laplace theorem. I'm going to go ahead and stop. However, in the rest of the notes, you will find the justification for the approximation for ln of 1 plus y. Thanks so much for sticking with me to the end. I really appreciate it, and I hope that you got something useful out of this proof. I'll see you next time where we work an example involving Brownian motion. Have a great rest of your day.